All right, let's just jump right into it. Welcome to today's explainer. If you're studying for your CCNA or Network Plus exams, or maybe you just want to understand how the internet actually works under the hood, you are in exactly the right place. Today, we're demystifying one of the absolute most critical parts of the four-layer TCP/IP model, the transport layer. We're going to break down these complex concepts into simple, visual, and highly testable pieces of information. So grab your mental highlighters because we are going to cover the exact concepts and scenario-based questions that professors and examiners absolutely love to ask. Let's start with a classic networking exam scenario. Picture this. Your computer is receiving a massive stream of ones and zeros from the internet. You've got a YouTube video playing, a multiplayer game running, and an email downloading, all at the exact same time. The data reaches your computer perfectly. But here is the million-dollar question. How does your device actually know which piece of data goes to your web browser, which goes to your game, and which goes to your email client? Because if it mixed them up, your game would crash and your email would literally look like raw video code. To answer that, here's our roadmap for this explainer. 1. The transport layer basics. 2. TCP, the reliable courier. 3. UDP, the speedy alternative. 4. A TCP versus UDP showdown. 5. Ports and applications. And 6. A lightning quiz. Let's kick things off with Section 1, the transport layer basics. To get the big picture here, you have to remember that the TCP/IP model has 4 distinct layers: application, transport, internet, and network access. Today, we are entirely focused on layer number 3. So what is it exactly? Well, the transport layer is the crucial link that manages end-to-end communication between specific applications on 2 different devices. And I really want you to notice that word applications. The layers below this one, like the internet layer, they already did the heavy lifting of getting the data across the globe to your specific laptop. But the transport layer's entire job is to take that data, once it actually arrives, and hand-deliver it to the correct application running on your screen. It handles segmentation, error checking, and flow control. And this comparison brilliantly illustrates the exact difference between IP and the transport layer. This is a classic Professor Pop quiz topic, by the way, so keep this visual in mind. The Internet Protocol, or IP, simply asks where. It delivers the packet to the correct device address. Think of IP as the postal truck finding your house. But the transport layer, it asks which application. It delivers the data to the specific program. Think of the transport layer as the person inside the house sorting the mail and handing the correct letters to the correct family members. Moving right along to Section 2, TCP, the reliable courier. TCP stands for Transmission Control Protocol, and it is literally the backbone of internet reliability. Just look at how it behaves. First, it's connection-oriented. That means before it sends even a single drop of real data, it formally introduces itself to the receiving device to establish a secure connection. It's incredibly reliable. It guarantees that packets arrive in the exact sequence they were sent, and if anything gets lost along the way, it actively retransmits that lost data. This is exactly why when you load your bank's website or download a PDF, half the page doesn't just randomly go missing. TCP makes sure every single bit is accounted for. So how does it actually establish that connection? Through a process called the 3-way handshake. You're definitely going to want to highlight this for your exams. Step 1, the client sends a SYN packet, which stands for synchronize, basically saying, hey, I'd like to connect. Step 2, the server responds with a SYN-ACK packet, meaning I acknowledge your request and I also want to synchronize with you. And finally, step 3, the client sends an ACK packet, confirming the connection. Awesome, let's talk. Only after this whole handshake is finished does the actual web data start flowing. All right, let's test your active recall here. We know TCP uses that elaborate handshake to guarantee a connection. But, the internet is chaotic. Wires go bad, routers get overloaded. So what happens if a packet of data is just inevitably lost in transit while you're using TCP? Well, it's automatically retransmitted. The receiving computer actually sends an acknowledgement for every single packet it gets. If the sender doesn't receive that acknowledgement in time, it just assumes the packet dropped and sends it again. TCP absolutely guarantees data delivery. Oh, and when the whole conversation is over, TCP doesn't just ghost the server. It sends a formal FIN packet, short for finish, just to politely close down the connection. Next up is Section 3, UDP, the speedy alternative. Now, sometimes all that point handshaking just takes way too much time. Enter UDP, or User Datagram Protocol. Compared to TCP, UDP is kind of the Wild West. Check out these characteristics. It's connectionless. There's no three-way handshake here. It just starts blasting data at the receiver whether they're ready for it or not. And because it strips away all those control mechanisms, it is lightning fast. But it offers zero guaranteed packet sequence, and crucially, there is absolutely no retransmission of lost data. If a packet drops, it is gone forever. UDP honestly doesn't care. Which leads to a really fantastic scenario-based question. If UDP is supposedly so unreliable and literally loses data, why in the world would major applications like online multiplayer games, live video broadcasts, and internet phone calls intentionally choose to use it? Here's the bottom line. It's because a 1-second delay is infinitely worse than a tiny bit of data loss. Think about it. If you're watching a live football match or playing a super fast-paced online game, and a single packet of visual data gets lost, your screen might drop a frame or glitch for a literal millisecond. You'd barely even notice it. But if the system used TCP and stopped the entire live broadcast just to go back and retrieve that one missing frame, your game would freeze up and you'd experience terrible lag. For live action, speed absolutely trumps perfection every time. Let's look at Section 4, TCP versus UDP. This right here is perhaps the most important foundational knowledge you can take away from this explainer today. Let's walk through this side-by-side comparison matrix. Honestly, take a mental snapshot of this table. TCP is connection-oriented, making it slower, but its reliability is incredibly high. So it's the absolute best choice for web browsing, sending emails, and transferring files. Basically anything where data integrity is the top priority. UDP, on the flip side, is connectionless, making it blazing fast, but its reliability is low. That makes it perfect for gaming, live video, and VoIP calls, where dropping a packet is totally fine, but any delay is a deal breaker. Oh, and examiners love to test your vocabulary on this next point. When the transport layer chops up the data to send it out, the resulting data units actually have different names depending on the protocol you're using. If you're using TCP, that chunk of data is officially called a segment. But if you're using UDP, it's called a datagram. Remember, TCP segments, UDP datagrams. Lock that in. Moving to Section 5, ports and applications. We know these protocols deliver data to the right device, but how exactly do they label the specific applications? Well, that's where ports come into play. A port number is a 16-bit number that acts as the specific key to find the correct application on a device. It's kind of like an apartment number in a massive building. The IP address gets the data to the building itself, but the port number tells the data exactly which apartment door to knock on. And since it's a 16-bit value, you actually have a maximum of 65,535 possible ports on your device. Pretty wild, right? Out of those 65,000 plus ports, a few standard ones act as universal doorways. Treat this table like your must-memorize checklist for literally any networking exam. Unsecured web traffic, HTTP, uses port 80. Secure web traffic, HTTPS, uses 443. DNS, which translates web addresses, sits on port 53. FTP, for file transfers, uses 21. And SMTP, which handles sending emails, uses port 25. Seriously, memorize these mappings. They will absolutely show up on your tests. And finally, Section 6, the lightning quiz. Okay, let's see how much you've absorbed today with a quick rapid-fire scenario. Think really carefully about what we discussed regarding speed versus reliability. Which protocol does sending an email use? And more importantly, why? I'll give you a second to think about the true nature of an email. And the answer is TCP, because you simply cannot afford to lose even a single letter in an important message. An email is essentially just a file transfer. If UDP were used and a packet dropped, your boss might receive an email that's missing the word "not" in a really critical sentence. Data integrity is absolutely paramount there, so TCP steps in with its reliability, sequencing, and error checking to guarantee the entire message arrives flawlessly. You've done an awesome job mastering the transport layer today, from end-to-end communication to the three-way handshake and the vital differences between TCP and UDP. But as we wrap up this explainer, I want to leave you with a slightly provocative thought about your own computer. We just learned there are 65,535 ports available. Right now, as you're sitting here taking this all in, how many of those doors are your apps secretly keeping open to the internet? If you're curious, I highly encourage you to open up your command prompt and poke around your own network activity. Keep learning, keep questioning, and I'll catch you in the next explainer.